Hello again from Digicool Things. Now for something a little different. I've always enjoyed playing with OLED display panels. OLED displays are generally much more expensive than equivalent sized LCD displays, but the quality of an OLED display generally exceeds the quality of a typical LCD display. OLED has sharp, clear pixels and inky blacks when the pixels are turned off. This is unlike LCD, where backlight-driven displays turn blacks into greys and colours generally just don't pop like they do on an OLED display. This project has also been driven by my early days. My first graphics-capable computer had a relatively low-resolution monochrome bitmap display. In those early days, we generally used an old CRT television, which we fed with either an RF signal through the aerial socket, or we modified it for a direct composite video input. I have fond memories of my first video display capable computer, which was the 1979 Dream 6800, published in the Electronics Australia magazine. It was also my first introduction to a high-level language. Well, it was higher level than the machine code I was using at the time. The Dream 6800 included a Chip 8 interpreter, which was originally implemented on the RCA Cosmac VIP system. Chip 8 was a language originally based around a 64 by 32 pixel graphic display, which both the Dream 6800 and the Cosmac VIP computers implemented via a video connection to a CRT TV or video display. With this background in mind, the modern availability of OLED display panels providing a really nice OLED quality, self-contained 128 by 64 pixel graphic display was something we couldn't even imagine back in the late 70s, early 80s. Certainly, it is something we would have died to get our hands on back then. So, given our MECB standard board size, I've chosen a really nice 2.7 inch 128 by 64 OLED display panel, which fits nicely onto an MECB card. This makes an all-in-one 128 by 64 graphics OLED display card for our experiments and retro recreations. It has also definitely occurred to me that this display card could even be used to create a self-contained Chip 8 based system as either the original 64 by 32 resolution or in a high resolution 128 by 64 Chip 8 recreation. Of course, it could also be used as a self-contained integrated display for displaying anything you like. The SSD 1327 controller that the display module uses also allows 16 shades of grey, that is 4 bits per pixel, so you're not just limited to on and off pixels. I've also chosen to use a green version of the OLED display, which nicely replicates the early green screen monochrome computer monitors. These were popular for reducing the eye strain originally caused by staring at white phosphor TV screen images for too long. So here's the final version 1.2 schematic for my MECB OLED Display 128 by 64 card. To work with our 8-bit retro systems, these display modules are available with an 8-bit interface. Now, I should explain how I got to version 1.2 already. Unfortunately, these display modules don't come with a datasheet. You basically just know the driver IC that the module uses. As mentioned earlier, this module uses a SSD 1327 controller, which the controller's datasheet notes as a 3.3 volt logic level device. The OLED panel's connections are also labelled with VDD for the power connection. Therefore, powering the panel with 3.3 volt power was my assumption. So, in my usual overconfident way, given that this is a relatively simple interface design, I dived straight into designing a version 1.0 prototype PCB. This was based on a circuit using a retro-friendly 3.3 volt regulator and 3.3 level shifters for interfacing to a 5 volt TTL level bus. And it didn't work. Since I'm always getting taught another lesson, let's just say this is a good reminder. Sometimes it just makes sense to breadboard your circuit ideas first. With some Googling, I finally found a schematic for the OLED panel, found on the original manufacturer's website. Here it is. As you can see, there are a couple of key things to note. Firstly, the module is in fact 5 volt powered, with onboard regulators for the 3.3 volts and other power needs. I should have noticed this, but I actually designed the PCB before it even received the OLED modules. Secondly, you'll note that the 3.3 volt logic level interface is implemented by a simple series resistors. This is probably okay for interfacing to a regular I/O port, but not ideal for directly connecting to our bus. So we do still need to include some buffers to appropriately interface to our bus. It was definitely time to break out a breadboard and an MECB prototype card to properly test the design, which is, of course, what I should have done in the first place. And here's a photo of my properly done breadboard test. Despite this now working perfectly, and having already designed and ordered my new version 1.1 PCBs, I then decided on one further design change, just to satisfy the perfectionist in me. This was because I had logically used TTL 74245 bidirectional buffers for the data bus and 74244 optical buffers for the address and control signals. These are the typical TTL bus buffer chips that we've always used for interfacing our 8-bit microprocessor creations. But after completing my version 1.1 design, I noticed that the 245 bidirectional buffer chips are now much cheaper these days than the 244 unidirectional octal buffers. So, as I thought it was more maker-friendly to just use two 74HCT 245 bidirectional buffer chips instead of two different chips, I redesigned again for version 1.2. So here we are at the third and final version of this seemingly simple project. So here is the final version 1.2 schematic. You can also see that in addition to the standard glue logic PLD, we have just two 74HCT 245 bus buffers, which isolates the OLED panel's series resistor level translation from our 5 volt TTL level MECB bus. So here is the PCB 3D render of our final routed version 1.2 PCB. As you can see, the OLED module fits nicely on the standard MECB card size. I've used a PCB header and provided holes for PCB standoffs to enable mounting the display directly onto the MECB card. So, on my workbench, you can see the first manufactured version 1.2 PCB and all of the components needed to fully assemble the display card. On my Tindie store, I'll be making available the PCB and some optional packs, which together provide all of the parts to make a full kit set. So let's get the first one assembled. So I'll start with the IC sockets. Right, next we'll do the female header strip. So then we'll do the bypass capacitors. And finally, the DIN bus connector. And here is the fully soldered PCB. Next, I'll get the OLED module plugged in and nicely mounted with its PCB standoffs. Note that these are M2.5 standoffs, which I supply in the hardware pack as white standoffs to easily differentiate them from the usual black MECB M3 standoffs. So I might mount them to the PCB first. Right, now I can grab the OLED display and drop it into its header. So it's nice and flush. And then we can screw in the 4 remaining screws. The standoffs are white, but I still include black M2.5 screws because they don't stand out as much. White screws would be a bit obvious. These are 5mm long M2.5 bolts, nylon bolts. And the standoffs are 8mm long, which is just the right length for these round pin headers. Right, so all secured in place. Okay, with the OLED panel mounted, I'll now fit the 2 dual inline ICs that provide the bus buffering. That's 74HCT 245s. So I'll just grab my pin straightener. Finally, we have the PLD for our address decoding. I've chosen to locate the OLED display card at IO address block 88 to 8F, being just above the 80 to 87 that I previously allocated to my VDP display cards. These different display cards can therefore happily coexist in an MECB system. So here's the PLD address decode logic. As you can see, I've used all 3 outputs of our standard ATF16V8 PLD configuration. 2 are used for independent read or write OLED panel signals, while the 3rd output is used for a general OLED panel select for enabling the 74245 buffers. So let's get the programmed PLD inserted. For the purposes of showing the card in operation on my video, I'll insert it into the horizontal backplane connector, so it's in clear view of my overhead camera. Later, I intend locating it in the front vertical socket of my backplane's bus connectors to make it a nice built-in MECB system display. So I'll use 2 of the standoffs just to hold it for the horizontal position. Now I can insert it into the backplane horizontal connector. I'll just move these out of the way. I can slide this over a bit. And lastly, it's probably time to take off the screen protector. Right, and we're ready. For the initial test, I've written some 6809 code to initialize the display panel and display some simple diagonal lines. All we need to know at this stage is that our display is working correctly and that we can control it with our retro 8-bit MECB system bus. So let's take a quick look at the code. Rightio, here you can see a OLED 128x64 test. First I've got a few equates, the entry point of 0100, the OLED address of C088, the OLED registers, the command register is at the OLED address and the data register at the OLED address +1. Then I set a value for the top of the stack and an X coordinate and Y coordinate, and finally an OLED resolution flag, which I use to signify whether the routines are treating the display as 128x64 or 64x32. Then we have the code entry point. I'll just scroll up where we have the usual 6809 initialization by first setting the direct page register, then setting the stack pointer. Then I go on to initialize the OLED display panel. Now there are a number of settings in the SSD1327 controller. However, I just initialize a few of the commands that are relevant, and you can see those if I scroll down. We have 16 bytes we send, which are 8 commands with various settings, which will be reasonably self-explanatory if you read the SSD1327 datasheet. So scrolling back, after I've loaded the initialization commands, I clear the display buffer, which is VRAM inside the controller chip. Then I turn on the display and I set the default OLED resolution flag to the default mode of full resolution. Then I have some commented out code that would fill the display with all pixels on, which we're not doing for this test. So if I scroll forward, you can see I now draw some diagonal lines. First I do 2 full resolution lines, diagonal lines on the left of the display, and then I draw 2 half resolution lines on the right hand side of the display. And finally I just return to a Sys09. So here's the data structure that I showed you before with all the initialization commands. Then we have some subroutines. Simple subroutine to set a pixel, which you call by setting the X and Y coordinate, dependent on the OLED resolution flag you've set. Then I have a clear pixel subroutine to turn off a pixel. And finally we have a toggle pixel subroutine, which is just designed to basically invert the pixel at the X and Y coordinate. And finally we have OLED fill, which is designed to just fill the OLED display with a given byte from a specified start row. So if you have start row of 0, you basically fill the entire screen with a specified byte. And beyond that we just have a number of support subroutines which support the routines I've just shown you. So this simple test can be found on the GitHub repository. Okay, so let's apply power and I'll transfer the assembled code over. Now I can run it with G0100. And all is looking great. Well, I should point out that the display is perfectly clear and rock steady to my eyes. Unfortunately, my camera capture is not synchronized with the OLED's refresh rate, so you can unfortunately see refresh flicker in the video recording. But you can trust me when I say that this is only visible on the camera. The display appears perfect to the naked eye. So now that we are up and running and we have some initial 6809 assembly drivers for our display card, I'm feeling the urge to relive some retro nostalgia and have some fun. But for now I'll just leave you with a small clue for what I'm now working on recreating. More to come. That's it. Thanks for watching.